In what is going to follow, we shall repeatedly need this particular improper integral from 0 to infinity of x to the power alpha minus 1 e to the power minus x dx, where alpha is strictly positive. Now let's take a look at the plot of the integrand. If alpha is greater than 1, it behaves like this. If alpha is equal to 1, then it behaves like this. And if alpha is less than 1, there is improperness at both the ends. Now you should know from your analysis class by comparison with e to the power minus x in the t's tail, and in case comparison with 1 by x to the power 1 minus epsilon, that this improper integral always converges. Clearly, the value of the integral in general will depend on the alpha. In other words, it's a function of alpha. We call this function gamma. This is the capital letter gamma. It is an interesting fact, though quite non-trivial to prove, that this function cannot be expressed in terms of any of the known functions, algebraic, trigonometric, exponential or logarithmic. That is why we treat it as a completely new function with a new notation for it. This function behaves much like the factorial function. In particular, we have this theorem: for all x, gamma of x plus 1 is x times gamma of x, which is very similar to n factorial equals n times n minus 1 factorial. Indeed, we have gamma of n equal to n minus 1 factorial for any natural number n, 1, 2, etc. Now, proving this fact is straightforward. Just apply integration by parts here. For this one, you just use this repeatedly and you start with showing that gamma 1 equals 1, which is trivial because once you put alpha equal to 1, this vanishes. This is just the exponential density, so it is 1. Now use this repeatedly like this to prove that. So the proof of this is pretty straightforward. The gamma integral motivates the definition of the gamma distribution. Defined like this, we shall say x has gamma distribution with parameters p and alpha if it has density given by this. This is very much like the thing that we saw, except for I have this px. And the constant is computed so that the total integral is 1. We know that such a constant must exist because it looks so much like the gamma integral. Let's quickly compute this constant. C must be the reciprocal of the total integral. So, if I substitute u equal to px, then I shall have, by the way, we are working with alpha greater than 0 and p greater than 0. That's why this will remain 0 to infinity. U by p whole to the power alpha minus 1, then this becomes e to the power minus u, dx becomes du by p. Collecting all the p's, we have alpha minus 1 here and 1 here, we get 1 by p to the power alpha times the integral, which we immediately recognize as the gamma integral. So it is gamma of alpha divided by p to the power alpha. Its reciprocal is c, so we can write it down as p to the power alpha by gamma alpha. The presence of the p here is much like the presence of the parameter in the exponential distribution. So this p is called the rate parameter and the alpha is called the shape parameter. In our notation, we have written the rate first and shape next, but in certain books we will find them in the opposite order. And remember, both of them must be positive. This is why alpha is called the shape parameter. When alpha equals 1, you get just the exponential. When alpha is less than 1, of course greater than 0, then it is unbounded here. And when alpha is greater than 1, you get like something like a knee. P, the rate parameter, only controls how fast the decay is. Higher P, the faster decay you have. We know how to integrate any function of the form which is a power of x times something e to the power minus some x in terms of the gamma integral. Now the gamma density already is of that form, some power of x times an exponential. If you multiply this with further powers of x or further exponential, it will still remain in this form. As a result, it is quite easy to compute the various moments of the gamma distribution. For example, expected value of x is integral of the density times x, which is absorbed into this power, and this is again something like the gamma integral once I write this as alpha plus 1 minus 1. This is exactly like our original thing, except that alpha is now replaced by alpha plus 1. So we know what this integral is going to be. It will be reciprocal of this, but alpha replaced by alpha plus 1. P to the power alpha 1 comma alpha plus 1. One cancellation is immediate, and also we know from property of gamma that this will also cancel, because gamma alpha plus 1 is alpha times gamma alpha, cancel, and you are left with alpha upon p. Using the same technique, you can also find expected value of x squared. Then in place of alpha, you will have alpha plus 2, or any x to the power k, you will have alpha plus k. And after suitable manipulation, you will get a product of alpha plus 1, etc., etc., and appropriate power of p. In this exercise, you have to work out expected value of x squared, and from this you will have compute variance of x. Remember, we just now computed expected value of x is alpha by p. Use the same technique. This is the density for your ready reference. So the integral of this from 0 to infinity is 1. So you can just substitute things and get the answer.